And this is the beginning of part 4. We're in Psych 400 Course Pack, Chapter 16, SEM I Path Analysis with Manifest Variables. This is part 4 of my video series on the chapter. At our last video, I had left off on page 20. We had shown this table of results that gave a bunch of statistics, a bunch of global fit indices for Model 1, which was Dr. O'Day's initial theoretical model, Model 2, which had one more arrow, Model 3, which had one more arrow. She concluded in looking at these analyses, Table 16.2 shows that of the 3 theoretical models being compared, only Model 3 displays an acceptable fit to the data. That's good news for Model 3, but we're not finished with our analyses. We have a bunch of other things we're going to look at. At the bottom of this page, which is page 20, at the bottom of this page 20, this video resumes where we left off the previous video. We resume by talking about the chi-square difference test. An earlier section indicated that when feasible, it's best practice to compare alternative models that reflect different theoretical perspectives. It's ideal if these models are nested, because the fit of nested models can be directly compared by using a special application of the chi-square test, the same chi-square test that you learned about in elementary statistics. We'll use that for comparing different models in path analysis. I'm on page 21 at the top. What do you mean nested models? A simpler model is said to be nested within a more complex model if deleting one or more paths or other parameters from the more complex model results in the simpler model. Given this definition, you can see from the figure 16.3 that Dr. O'Day's Model 1 is nested within Model 2. You know that those models are nested because Model 2 is identical to Model 1, except that it contains one additional path, the dashed line arrow from lack of time for exercise to exercise sessions. Model 1 is essentially just the simpler version of Model 2, and that means it's nested within Model 2. What is he talking about? We're on page 21. Let's take a look at this theoretical model. Disregard the dotted line arrow for the moment. Right now, just pay attention to Model 1, which is the model that consists of all of the solid line arrows, and Model 2, which is identical to Model 1, except it also has this dashed line arrow. Model 1 is nested within Model 2. That's because Model 1 is basically a simpler version of Model 2. You begin with Model 2 that has all of these arrows, including the dashed line arrow. That's Model 2. If you got rid of the dashed lined arrow, you'd be left with Model 1. That tells you Model 1 must be nested within Model 2. That's what we mean by models being nested within one another. We continue on page 22, the logic of the chi-square difference test. Adding a new path to a simpler model almost always improves the model's fit to the data. However, in many cases, the improvement in fit is only trivial in size. Making matters worse is the fact that adding a new path will certainly make the model less parsimonious, and a less parsimonious model is usually less desirable. Therefore, researchers typically want to add a new path to a model only if adding that new path results in a substantial improvement in the model's fit to the data. Because of these considerations, researchers sometimes perform a significance test to help determine whether adding the new path to the existing model results in a statistically significant improvement in the model's fit. This significance test is the chi-square difference test, and it's based on the chi-square difference statistic, symbol delta chi-squared. Remember delta? We learned about this in a chapter on multiple regression. The symbol delta is typically used to represent a difference or an increase. In this case, delta chi-squared is going to be our symbol for the chi-square difference test. I'm still on page 22. The chi-square difference test. To compute the difference statistic, the researcher begins with model chi-square statistic for the simpler model and subtracts from it the model chi-square statistic for the more complex model. The result is the observed chi-square difference statistic, symbol being delta chi-square. To determine whether this delta chi-square statistic is statistically significant, the researcher looks up the critical value in a table of chi-square in the back of a statistics textbook. The degrees of freedom for this test are equal to the number of paths in the more complex model minus the number of paths in the simpler model. If the observed delta chi-square statistic is larger than this critical value of chi-square, it means that the addition of the new path to the model resulted in a statistically significant improvement in the model's fit to the data. In other words, if the results are statistically significant, it means that the complex model provides a fit that's significantly better than the fit displayed by the simpler model. Let's begin by comparing Model 1 to Model 2 in our current analysis. Comparing Model 1 to Model 2. Table 16.2 shows that the model chi-square statistic for Model 1 is 15.34, and the model chi-square statistic for Model 2 is 18.90. Now, where did those statistics come from? Let's go back to Table 16.2. Table 16.2, yes. Table 16.2, Model 1 under the heading chi-square. Model 1, chi-square statistic is 51.34. In the same table, for Model 2, the chi-square statistic is 18.90. That's where the chi-square statistics come from. Now let's go back to the test that's being described on page 22. Comparing Model 1 to Model 2, I went through all of this. Chi-square statistic for Model 1 was 51.34. Model chi-square for Model 2 was 18.90. Subtracting the latter from the former results in a chi-square difference statistic of delta chi-square being equal to 32.44. Model 2 has one more causal path than Model 1, and this means that the chi-square difference test has 1 degree of freedom. A table of chi-square indicates that with alpha set at 0.05, the critical value of chi-square with 1 degree of freedom is 3.84. This is the value of chi-square that you would get in a table of chi-square in the back of any statistics textbook. So, critical value of chi-square is 3.84. Our obtained delta chi-square statistic is 32.44. What does this mean? Because the observed chi-square difference score, 32.44, is larger than the critical value, 3.84, Dr. O'Day concludes that adding the dashed line path to Model 1 resulted in a significant improvement in the model's fit to the data. In other words, Model 2, the more complex model, provides a significantly better fit than Model 1. So, to put this in visual terms, think of Model 1 as being the version of the model that has only solid line arrows. If we added this path, it goes directly from lack of time for exercise to exercise sessions, this dashed line path, it results in a statistically significant improvement in the model's fit to the data. That means Model 2 gives us a better fit than Model 1. That was our comparison of Model 1 and Model 2. Let's go to page 23, new paragraph headed, comparing Model 2 to Model 3. To put this in visual terms, what's the difference between Model 2 versus Model 3? Model 2 is the model that consists of all the solid line arrows and also has this dashed line arrow. Model 3 is identical to Model 2, except that it has one additional path. It has this dotted line path that goes from dislike of exercise to health motivation. Does adding this path result in a statistically significant improvement in the model's fit to the data? We will find out in this section headed Comparing Model 2 to Model 3. Again, this is on page 23. Table 16.2 shows that the model chi-square statistic for Model 2 is 18.90 and the model chi-square statistic for Model 3 is 5.85. Subtracting the latter from the former results in a chi-square difference statistic of delta chi-square 13.05. This observed chi-square difference score, 13.05, is larger than the critical value, 3.84, so Dr. O'Day concludes that adding the dotted line path from dislike of exercise to health motivation resulted in a significant improvement in the model's fit to the data. In other words, Model 3 provides a significantly better fit than Model 2. Put it in visual terms. Yes, the most complex model, the model that has the solid arrows, the dashed arrow, and the dotted line arrow, that model provides a significantly better fit than any of the other simpler models. Let's continue where we were. Page 23. Page 23, near the bottom of page 23. We come to a new statistic. R-squared statistics for the competing model. That'll be a good place to begin our next part. And this will be the end of part 4, and we'll begin part 5 with R-squared statistics for the competing models.